Hey everybody, it has been a few weeks since we have actually gotten spoke about any of the course material. I'm hopeful that not everybody has completely forgotten what we've been talking about or at least can quickly reference and remember going into exam 3. So this is my first attempt at making a video for the course. I don't believe in redoing any of these because it takes a lot of time. So I'm sure I'm going to mess things up, and we will figure it out, ignore it, and move forward. I had to take over one of my kids' bedrooms as a second office in my house now that my wife is also working from home. So I wish I had a fancy background like you see the people on TV have, but I don't. The life of a grad student. With that, I do have kids, and I have a large barking dog, so we might get interrupted from time to time doing these presentations, but oh well, no big deal. All right, so as a quick refresher, where we ended was on chapter 7. I know at the top of my slides you see 4.5 or whatever it may be. That's because I work from a different textbook than you guys, and I try to make sure that I'm in the right sections at least. So if you see a 4, put a 7. Most importantly, just look at the title whenever you're referencing your book, making sure that they do indeed match. And most of these should be correct. So where we ended, at least for those that I think most people came to our final lecture starting in chapter 7, was plate tectonics. We had talked about kind of theories of continental drift and kind of the first ideas stating that continents do indeed move and they're not pinned into one geographic position. I hope this kind of makes sense, and kind of how to where we got today with the theory of plate tectonics. So the last lecture where we ended was on divergent plate boundaries and seafloor spreading, right? So reference your book, reference your notes, just to get that back, because I'm not going to redo the lecture on that. If you need help, please use our time together on Wednesday, this Wednesday, or any future ones to get a refresher and to ask those questions. Okay, so today, before we talked about, again, divergent plate boundaries were essentially the plates, right? So tensile plates move apart, and whenever they move apart, they're moving apart at the mid-oceanic ridges, and by doing so, it's allowing mantle material, so like lava, to rise to the surface to create new Earth, right? So this process is always occurring. So the question is, if lithosphere is always being created, right? So separation of the plates is always occurring. It's creating new land, but why is the Earth not getting larger, right? If we're always creating new Earth, right? And so the simple answer to that is simply that at the same rate that we are creating Earth, Earth is also being destroyed or recycled, right? Earth's not certainly being destroyed, right? We're never really destroying matter, but on the other side of a plate separation, you also then have plate being subducted or sinking back into or towards the Earth's core, so into the mantle. So the basic process is simply, if we look at this chart here, and I apologize, I made a big yellow pointer hoping it would be helpful. If it's not, if it's kind of distracting, let me know and I'll find something else. But we have a plate in this example essentially subducting or going underneath the other, right? So this is the Juan de Fuca plate, which is off the west coast of the US, and then you have the North American plate, right? Excuse me. So that's just the basic idea. And a lot of these that we're going to talk about, I'm going to repeat kind of over and over and over. And it kind of holds across the different forms of evidence and processes that we're going to see. Also, so what you notice at the bottom, my little video of myself here, I have no idea how to move this. to get it out of the way. So it's currently covering up notes, but what I can do is click it to make it go away and make it come back. So periodically I'm going to move it so that you can actually get your notes, right? For the exams, I am trying to really stay to what I'm saying in the written component of the notes. So make sure you're getting these down. That's really the most important thing. Like, I'd love for you to actually listen to me and learn something from what I'm saying, but if you're writing down everything I have here, you're going to be more than okay on the exam. Okay, anyways, so we have two plates, right? They're intersecting. They're moving towards each other in some way. They're intersecting. So the question is, what determines which plate subducts or goes underneath the other, right? So we talk about this as kind of a generic question we had, weeks ago. It was something kind of off topic, but we talk about like the continents, like why is some lithosphere, why is some crust, why is some land above the ocean, and why is some below? I mean, I feel it's a fairly simple kind of question. And it's simply the fact that the subducting plate is always essentially denser than the plate it's subducting underneath, right? So in this particular image, we have kind of this oceanic plate colliding with a continental plate. And what we know about these oceanic plates is that they're incredibly dense, right? They're basaltic by comparison to your continental plates, which are mainly granitic, right? So these two plates in this particular example, they're colliding, and the one that's going to go underneath is always going to be the one that's the most dense. At the same time, the subducting plate is able to subduct because it's also denser than the asthenosphere underneath it, right? So this orange piece here, right? On average, the plate above is 2% denser than the asthenosphere below. If the densities were the same, the subduction would be minimal or wouldn't even be allowed. All right, let me move this here. If I can figure out how to move it. There we go. Okay. The book also we talk about the angle of subduction. So in this particular example where the plate dives down below, the different trenches within the ocean, they're all different depths at all different angles. And the question is to, why the differences in depths and why the differences in angles. And it's simply a relationship to density and also age basically being the same thing. So if we recall, at your mid-oceanic ridges, right, that's the production zone of new lithosphere. As they spread, as they create new land, older land moves away, right? It spreads away from the particular ridge. And so the longer this process takes before it hits an actual subduction zone, this land moves further and further away. When it does that, it cools, right? Because it's interacting with colder ocean water, so it's cooling. When it cools, it becomes denser, right? Excuse me, I have a cold myself. So these denser, older lithospheric plates have a tendency that when they hit the subduction zone, because of the density, they have a much steeper gradient. They dive down similar to this graphic here at a steeper angle compared to a younger one. In the Western Pacific, you have these really deep ocean trenches at near 90-degree angles. So imagine essentially walking towards a cliff, right? So this plate at this trench will dive pretty straight down, pretty dramatically into the asthenosphere. Whereas kind of on the eastern side of the Pacific, you have much younger lithospheric plates. And so their descent into or underneath the other plate is a much more gradual angle. And this is generally just a function of distance, right? So if we think of the ocean spreading in the Pacific, the mid-oceanic ridge is much further away from the western portion of the Pacific than it is to the eastern portion. And so it has, the western side has a longer period of time in which to cool, in which to become more dense than does the eastern side, where the mid-oceanic ridge is closer in proximity to the subduction zone on the eastern side. I have a note down here about read know the deep ocean trenches. The book has a sentence or two about it. I'm not going to get into it. Just generally know, this zone right here, that's your trench, is kind of the point of contact. And it refers to them frequently throughout the chapter, but nothing in any real great detail. So just generally know where they're located along these zones, and generally kind of what they mean, okay? So there's three different forms or convergences, I guess, along these boundaries, right? So we know, we have continental, we have oceanic plates, so therefore you can have three different convergences. So you have oceanic continental, continental continental, oceanic oceanic, right? So in this particular example, we're going to talk about oceanic continental convergence, and that is simply where oceanic plate converges with the continental. So as we talked about, and this is where some of this will start to become redundant, but the denser oceanic slab, the plate, is always going to sink underneath the continental, right? So it's really just a point of composition is the density, because it's a lot of basalts, a lot of irons versus your granitic, which are just not near as dense, right? So what's important in these examples, what we're going to talk about, is what's going to happen underground, right? And if I move my picture again, and what we're going to be looking at is kind of this creation of magma and its ascent towards the surface, towards the creation of volcanoes, volcanic arcs, and islands, right? So whenever a plate, oceanic plate, subducts underneath a continental plate, it brings with it a lot of water, right? So you have a lot of saturated rocks, and then when they're being forced down, they're being squeezed, and all this water comes out of the rocks. When you start introducing water in these high pressure environments, it has a melting effect, right? So the water acts as a chemical reactant to the water, to the rocks around it. And I put here, it's called partial melting, right? Because it doesn't melt in terms of like, just straight liquid, but it melts enough where it gets incredibly hot, and anything like we talk about, like especially in the previous sections within the atmosphere, you start increasing the temperature, you decrease the density. So if you're decreasing the density of this melted now, lava, it starts to rise to the surface. Or if I move my picture again, right? So we have the subduction plate bringing, rocks, but a lot of water with it. When the water gets down these high density, high pressure zones, it basically causes the rocks to melt, right? And this lava now will rise to the surface. And it has two possible kind of outcomes here. Primarily what's going to occur is this molten lava is going to rise, but it's also then going to cool, and it's going to turn back into a solid, contributing then to the thickness of the continental crust, right? So we see kind of this oblong shape here, the continental crust, and it's going to essentially just serve to thicken this. However, some amount of this this lava will actually escape to the surface, becoming, a volcano or volcanic activity. Excuse me. So we have, in this regard, I have up here continental volcanic arcs, and we'll talk about volcanic island chains and so on and so forth. But this occurs on the continent, where you have this, essentially we'll talk about in the next slide too, I think, this hot spot where the lava is coming up, well, the plate above is continuing to move, and you create these, this arc, this chain of volcanoes within the continental plate, right? And so the examples we have, this picture here is along the Cascade Mountains. So this is, California, Oregon, Washington. We have, I'm trying to remember what I even put here. So Mount St. Helens is probably the most obvious ones for most, the, super destructive volcanic eruption. We have Mount Rainier, which is in Washington, same thing as, Helens, and then also, geez, what did I even put here? Mount Hood, excuse me, in Oregon, right? So this is all part of this let me go back. I can't go back. This volcanic chain, right? And so this is really the point of which the Nazca North American plates are intersecting and having this effect where magma is now rising to the surface, obviously over incredibly long periods of time. All right, next we have oceanic convergence here. So the previous oceanic continental. Again, simply a function of one plate is subducting under the other. In the case of oceanic convergence, when we talk about oceanic continental, it's easy to say, okay, well, obviously the oceanic plate is going to subduct underneath the continental. In this particular case, is going to be the older crust, because it's going to be denser, is going to subduct underneath the newer crust, right? So again, it's just a function of age. So very similar processes as the plate subducts, brings with it a lot of water, right? It's in the ocean, bring a lot of water. You have this partial melting. The partial melting serves to allow magma to rise to the surface. It's either going to create a thicker crust, or it's going to escape all the way to the surface. You're going to have some sort of volcanic activity, right? So it's very similar ideas. It's just that where it's occurring and which two plates are involved. Our examples here. So you have your simple kind of your islands, right? And so basically, meaning if we go back to the previous image, where it's simply a function of lava rising to the surface, creating new landmass, because that's ultimately what it's doing, is cooling and creating rock. So the examples to that is like your Northern Mariana Islands. However, you have other examples where you could have had like previous oceanic crust that had broken off, or continental crust, and then it you have these hot spots where this activity has kind of essentially joined into these pieces that were broken, and they create much larger structures. So similar, the other comparison to like the Mariana Islands, where they're kind of small and not really structured, but you also have Japan, right? And so this was a function of previous crust that had broken off, and then you had essentially this volcanic activity building upon what had already existing and making it larger and larger, and then similarly to Alaska and the Aleutian Island chains, right? So these are our three examples for this. All right, so our last with our convergent plate boundaries is the continental. And this is essentially a function of, or a byproduct of, subducting oceanic continental layers to the point where then a portion of continental landmass that was on or behind that subducting layer ultimately intersects then with another continental boundary. So the example is India. Over 70 million years ago, the Indian continent was fairly far removed from the Eurasia. Over the course of the 70 million years, you had the subducting of the oceanic plate underneath the continental, and all that did was essentially serve to shorten the distance. So as it's subducting, it's basically pulling this continental landmass towards where it is today, right? So as the plate is being subducted underneath Eurasia, right, this continent, is there, it's kind of moving, but it's also pulling it towards it. The physical feature which you're going to find with these is that as these continents collide, you have a lot of rock deformation, and I think you can see this without me moving it. Yeah, there we go. And so, the most famous mountain range in the world was formed this way. The Himalayas, right here along this boundary here. And all that was essentially the two plates colliding together. And as we recall, And this is a smart figure from the book, so I'd suggest, looking at this. Obviously, it's not hyperlinked in this video, but it is in the book that you can type it in manually. But you have the two crusts, the two continental plates converging together. As they converge, because they're of essentially equal density, right? Now you don't have the dense oceanic plate, they're capable of diving below, they're essentially going to collide. Now, while some subduction is certainly going to occur, and in this image it's kind of like this bulbous piece here, the majority of the activity is going to occur essentially vertically, right? And so that's going to manifest itself in these, huge mountain ranges. So if, on the exam, if I'm asking a question about this, it'll be something more specific to, I'm not really sure how I'm going to ask it, but I won't say something like there is a minor detail here of that. Certainly subduction does and can occur, but it's very minimal, right? So I'm not going to, ask it in some sort of weird nuanced way like that. Just know that the convergence of these two continental plates, essentially, because they're of equal densities, the reaction is essentially these formation of these mountain chains at the surface. So my examples here, so the obvious one is always the Himalayas, right? We all know that. This really pretty picture down here, that's the Ural Mountains, and that's in like the western third of Russia. And I've been here before hiking. That's actually really pretty. And then, of course, closer to home, the Appalachians, right? And we talked about these at the beginning of the section in terms of like how do we start identifying kind of early ideas of plate tectonics and continental drift. But that's how these occurred kind of at one of the original formations of Pangaea. Now, I'm not sure, I make sure you know these examples, not just these, but all of them. I feel like those are kind of easy questions I can give you on the exams to get you some points. So make sure you're writing these down. Most of these, or at least some of these, are in the book, but make sure you're able to identify what some of these examples, what they are for the purposes of the exam. Okay. Again, especially with the transition and kind of the weighted point structure of these questions, not questions, excuse me, of the exercises and the exams, and now we're emphasizing the exercises, that I'm not trying to make the exams very challenging at this point because they're not weighted as much for one, but also there's just more opportunity, I think, for you to mess up on them, given that we're not meeting in class and you don't have as much opportunity to ask very direct questions. So anyways, so I'm going to try to find, easy ways to get you points, and examples are those. All right. Different form. So we had convergent, divergent plate boundaries, but also now we have a third form, and these are going to be your transform plate boundaries. So the differences between transform plate boundaries and the other two, this is a point where boundaries are interacting. However, there's no new crust being created or destroyed, right? So in divergent plate boundaries, we're creating lithospheric crust plates, but at divergent boundaries, we're destroying it or recycling it, right? In this particular case, we don't have any of that. We essentially have interaction via kind of, basically they're just sliding past each other. And I think we all, or you all have in your mind, the easiest, most famous example in the United States where this occurs, and we'll talk about that specifically here in a second. But really and we look at this image, that simply is just the identifying feature, is that the plates will do this, right? And so we get a lot of earthquakes out in California because we have a fault that is doing this at all, not back and forth, but it's doing this at all times, right? So it's that friction force. So within this image, if we're looking at it, and we move, yeah, so you can see the key here. So these linear features, so this is mostly found under the oceans, right? And obviously there's some on land, hence why, California, but mostly you'll see these under the oceans, but basically these linear depressions. So think of these as like, what we have obviously are these red lines here. These are spreading centers. These are mid-oceanic ridges, right? These are where your plates are pulling apart. But then we're also referring to them generally as fracture zones. So it's just that point of interaction. But this whole structure, the whole system is referred to simply as the fracture zone. Within these, we have two different faults, right? We have an inactive and an active zone. And you kind of work through this by looking simply at the arrows. So our active transform faults, they're generally thought, well, they do as defined, they connect active ridges, active spreading centers to one another, right? So if you follow my cursor here and then follow it to the next one, it connects these. And all it's simply doing is saying that adjacent plates are essentially moving against one another, right? They're not moving parallel to each other in the same direction. They're sliding like this, right? So if we follow these arrows, if we look at first the spreading center here, right? So this is the divergent plate boundary. This is your mid-oceanic ridge. And so Earth is being created, and as it's getting older and as it's creating more, right, everything's moving this way on this side, and then we go to the right side and everything's moving this way. Well, the same thing happens at all these different ridges, right? So follow this arrows moving to the left, moving to the right, moving to the left, moving to the right. Well, what happens is, because these ridges are occurring at different locations, you know, upstream, downstream from one another, they're not aligned. And what the lack of alignment does now is it creates plates that are just simply sliding against one another, right? So it's a pretty easy concept. Like if you were to simply align, if we took all of these ridges here and kind of squished them back together, you know, all the plates would essentially move in the same direction. But because of different rates of spread, right, and plate movement, like these aren't, all these things don't happen at the same intervals. You start getting, I pointed at the screen, not that you can see that. You start getting kind of this dislocation, right, where plates now are starting to kind of grind past one another. So that's the active. The inactive zones are simply kind of geologic artifacts of what, you know, occurred a long time ago. So these are points, unlike your active zones where they're sliding past each other, where they're now sliding in the same direction. And again, that's due to, you know, movements of plates, rates of movements. You know, so basically it's just showing what happened a really long time ago, right? So this is just geologic evidence of a long time ago. This used to be an active fault, right? It's just that these ridges and the plates, you know, everything's moved over periods of time. And so they've moved in such a way now where the spreading of this top ridge here, moving all the way to the left, has caught up with, you know, the westward or whatever this is, you know, spreading of this particular ridge. So once it reaches this point, it goes into, you know, inactive zone, and that they're both moving in the same, let me try it this way, the same direction. I hope that made sense. Here we go. So here's a GIF for it, right? So your mid-oceanic ridge, let me move my picture here, mid-oceanic ridge, right? We have the creation of the land, right? We have the upwelling of magma. As the plates move, general direction of on either side of the ridge, right? Here's your fault, as your active transform fault, and they're sliding simply past one another. If we were to continue the motion and we move it out, this kind of this northern, this top piece here, and move this all the way out, and, you know, complete some of the arrows here, everything out this way, everything's moving in the same general direction. The same thing, you know, right about here and out, right? So the frictional forces are here, and that's where like a lot of your earthquakes, your shallow earthquakes at least, are going to occur. So transform faults. All right, so again, another smart figure in your book. given, I would definitely view these. They're all only a couple of minutes each, but I think it'll go a long way to understand. A lot of these you could, I mean, really you could do, you can understand a lot just by watching these videos. They do a really good job of explaining everything overall. All right, the famous example is what? So some other examples the book talks about is the Mendocino Fault, that's in the Western Pacific, Alpine Fault in New Zealand. What is this fault? I know we talked about it before, and I think what I'm going to do is simply, this is going to be one of your questions for next Wednesday, is what is the name of this fault? Talks about it in the book. It's in the US, California. Can't make it really any easier than that. I love these pictures. I don't ever really know if these are actually real pictures or not. So obviously on the left we have a picture of the actual fault, right? So I know this is true, but there's all of these old pictures that I've looked. I remember during my master's looking at a lot of these, just kind of fascinated, where they show, because of the sliding of the plates, how like fence lines have shifted over time, right? And so presumably, if this is a real picture, this fence used to connect, but as the plates again slid past one another, they created these gaps. There's also a bunch of pictures like this for like roadways where they used to connect, or you can even still see like lines in the roads, and they'll do stuff like this. There's definitely a lot of these that are real, like post earthquake activity that you can find out in California. They're really cool. But I love like these old ones. They're fantastic. Okay, anyways, so remember, name of the fault. That's gonna be one of your questions for next Wednesday. All right. And no good scientific principle can't be explained using an Oreo cookie, because I love Oreo cookies, right? So I found this image, thought it was kind of silly. General idea, plates are sliding over your asthenosphere. Asthenosphere presumably is the cream here. Our three different boundary types, divergent plate boundaries, they're simply separating, right? So it's the person pulling the cookie apart from each other. Your convergent plate boundary are when they are colliding into one another, one of them is going to subduct. So this piece of the cookie here, subducting under the other. And then lastly, your transform plate boundaries, simply just sliding past one another in opposite directions. Probably should have thought of a question to do with the Oreo cookie, but that's what you get. All right. Next sections, there's what, 2 sections left. So testing the plate tectonics model. So what is the evidence? Like, why do we know, how do we know what we know, right? And so a lot of this started back in the 60s where, with development of technologies, we basically had the idea of testing the seafloor, right? Because the presumption was that the seafloor itself, one, was younger than continental crust, which it certainly is, but also at these spreading centers here, that this will be the younger portions of the seafloor, and as you move outwards, they get older. So back in the 60s, you had the deep sea drilling project, and they built a ship, the Glomar Challenger, huge ship, basically able to get core samples really deep down, in thousands of meters of water. And so that's what they did. They basically took, hundreds, if not thousands, of core samples from the ocean floor, and essentially mapped them. And what they're able to see is just what the hypothesis, let me move this here, just what the hypothesis suggests, that the further you get away from the mid-oceanic ridge, right, this point of spreading, that the seafloor gets older, right? You have, it gets deeper. It gets deeper because you have the depositional aspect of the sediments, right? So sediments get, displaced all the time, but obviously the longer seafloor is there, it has the ability to collect more sediments, right? So there's very little sediment present at the point of origin, right? So at the point of spreading, but as the further they got away, there was a lot of it. So it's thicker, right? So this thickness, that's why I have here, the thickness increases with distance from the ridge, so too does the age. It's the same thing, right? It's part and parcel. So when they were dating these, and so they used they couldn't use kind of your traditional radiometric style dating because of salt water is basically is destructive, right? So it changes kind of the chemical properties of the rocks. And so radiometric dating in these environments is not very accurate. And so what we had talked about before, they used other paleo methods such as, your fossil records, right? And so you could see the existence of fossils at different depths, at different distances to the spreading center. And so what they concluded is that, relatively, or comparatively to the continent, your ocean floors are actually quite young, the oldest being 180 million years old. That's what's in existence today. Yes, old, geologically, it is young. But by comparison, your continents are, a few 100 million years old, and the current known is 4 billion years old. So significantly older, right? And so the function of that, or the reasoning for that, is simply that your continents don't get subducted, right? So they're created and then they're there, right? I mean, you obviously have, erosive properties and things like that, but they hang around a very long time. All right. So more testing, more evidence. The evidence in this particular regard is your mantle plumes and hotspots. So this GIF is really good in explaining what these are. So a plume essentially is just, right, it's the magma flowing up from, somewhere deep in the earth. And we'll talk about, some of the models don't agree exactly where they come from, but let's just say somewhere within the mantle down to the core. But you have these, plumes of lava that are fixed, right? They don't move. But what does move is the crust above it. And so as the crust, the plates above it move, the intrusion of magma is continuous, and depending on the speed, well, I guess it's always flowing to the surface in some way, and depending on the speed, has the ability to create to build seamounts or even islands, right? So seamounts, if you recall, are ones that are, essentially these volcanoes, islands under the sea, and then once they rise out of the sea, they're volcanoes or islands. So anyways, so as the plate's moving, you're creating land above the water. I have a note here. This is a little bit different. We talked about partial melting before. Decompression melting essentially is just that idea that this intrusion of seawater decreases and the decreased pressure, meaning as the lava is rising, right? As it's rising, it has less stuff, less mantle product, forcing itself upon it. So you're decreasing the pressure, which then allows for more melting, and we're calling this decompression melting. So know the words decompression melting and partial melting, and that they're different in different environments, right? If you don't understand, please ask the question at some point, right, on Wednesdays or whatever it may be. But that's kind of an easy question to make for the exam. Okay, anyways, so that's your mantle plumes. Your hotspot is essentially just the physical manifestation of the work done via this plume, right? So the plume is just the lava, it's the magma that's rising to the surface. The hotspot is the islands themselves, it's the volcanoes. Again, it's the physical manifestation. Let me move this. We have hotspot tracks, and a hotspot track is simply just this chain. In this particular case, chain of volcanoes. Again, the crust is continually moving, and assuming this plume stays, it'll continue to create, these physical beings of volcanoes. As this moves, you're going to create a chain, right? That's all that is. There is a note here, important to note that these occur kind of mid-plate. They're not happening at the boundaries, meaning where the plates are coming together. These are essentially, if it helps you to think about it, essentially holes in the plate where, magma is rising at all times. Not really a hole, but you get my drift, hopefully. All right, move my picture on this. So this is the hotspot. right? And so this is kind of the natural cycle. We think of this primarily with Hawaii. Also, you have like the Galapagos, right? And so this top example here, you have this mantle plume, you have the rising lava, and it creates these, features, right? In this particular case, these volcanoes. The crust continues to move, so we follow this chain out, right? It just keeps producing. These chains can be enormous. The largest one that I think we studied today, there's like 100 and I'm going to get the number wrong, but it's like 130 volcanoes that stem from Hawaii. They go out to Midway, which is, central, Pacific Ocean up to the Aleutian Trench, which is kind of a sharp turn north in the Pacific. Either way, it's huge, right? And so this plume has been there a very long time. If you consider the distance that that the evidence and the remnants of volcanic islands are, right? I mean, that's thousands of miles, right? So in this particular example, we show kind of the life cycle, right, from creation over then a long period of time. These mounts get eroded basically away into nothing. Well, Hawaii, that's basically what's happening with Hawaii, right? So the youngest island in Hawaii is less than 1 million years old, right? That's the main island of Hawaii. Well, directly underneath this, that's the mantle plume, and you can tell the direction of the travel of the plate by essentially looking at the islands and their age, right? So in this particular example, right here, this would have been the first, at least in this little chain, this would have been the first land created. And then as it moved away, right, it starts then creating all these different land masses. And we can tell the age here, almost 4 million to 6 million years old, 2 to 3, 1.5-ish, and then less than Maui's a little bit less, and then, Hawaii less than that. So kind of cool. So that's how a vast majority of these islands are formed. And again, this particular island chain is enormous, right? Like I said, 140 or so odd islands extending from this hot spot, right? Well, this plume, right? This is the hot spot, and basically traverses over to the center of the Pacific up then to the north. And then one of the questions on your exercise talks about essentially how are you able to tell the direction of travel of the plate. And again, it's simply just looking at this island chain and then relating it to the age, right? And so you can tell that the plate, at least initially, is moving kind of this northwestward direction. And if you were to kind of zoom out on this map, you would notice that at some point it kind of takes a very sharp north turn, right? If you follow my cursor. All right, so how are we testing these things? How do we know kind of what we're hypothesizing is true? And there's a couple of different ways, and this is the last part of this this video. But the first one is paleomagnetism. If you recall, the idea of paleo something, it's really just a passive way in which we're investigating something that happened a long time ago, right? So I know we had talked about before, but I assume most of you know that the Earth has a magnetic field around it, right? And so magnetic field is caused by essentially the turning, the spinning of our, kind of solid iron core of the Earth, right? So it spins, it creates kind of this magnetism. So because of that, we have two different norths. And I know we've talked about this before. We have our geographic north, and we have our turn that back on, and we have our magnetic north. So they're not the same, right? Our geographic north doesn't change. It's kind of what we identified kind of socially as being north, but it's always in the same position. But our magnetic north, it does change, a bit, but they're generally located, let's just say, for sake of argument, kind of in the same general area, right? So the evidence supporting plate tectonics, this is probably the most important piece of evidence that we have. And it's just the idea that that magnetism itself is preserved within our rock structure. So when a rock is formed, it has magnetism in it. And because it has magnetism in it, it responds to the magnetism of the field of the magnetic field of the Earth. And then once that rock is truly formed and solidified, it maintains that orientation to north. And so if you think about like lava, right? So lava is liquid-ish, not liquid, but you get my point. As lava is flowing, in and of itself, it doesn't have any sort of magnetism, but as it solidifies, these iron-rich particles start to align themselves to north, right? Just like a compass of the needle of a compass, or if you're playing with magnets at home, right? If you're getting it close to like a metal bead or something like that, like it tries to either go towards the magnet, but at least it tries to orient itself. And so as the rock solidifies, orientation essentially will point to magnetic north. That's what all minerals do. And so, once it's then solid, I mean, unless it gets recycled back into the mantle of the Earth, it's going to point in that direction forever until it's disturbed or something, right? And we'll talk about that actually next week when we start talking about kind of get into rocks and rock cycles and whatnot. Anyways, so we can use these points of orientation to say, if or how things are moving, because if we find a rock and this orientation is no longer pointing north, well, something happened. And that's why I have here the paleomagnetic records there, right? All right, so then there's this idea of polar wandering, right? So if we accept the idea that rocks are magnetic, and that as rocks are formed, they're pointing to magnetic north. Okay, well, if we hold that to be true, but then we work backwards, right? And so if we look at this image here, and given present day magnetic North Pole here, right, just outside of Greenland, we have two different tracks. We have North American track here, and Eurasia here, right? So if we work backwards, and given the evidence that we find, we basically show the path and the distance that these giant landmasses, these continents, would have had to have traveled. The problem is these are pretty dramatic shifts in distance and orientation. It also shows a separation between North America and South America. So the question is, again, given the magnetation of the rocks, did our magnetic poles shift that much? Meaning the magnetic pole today would have been over here by Hawaii, 500 million years ago. Or, let me move this, was it essentially just the relationship of the continents to the pole itself? And all I mean by that is simply the poles weren't moving, right? And I mean, they move a little bit, and we can track it, and we do on a near daily basis, but it wasn't the poles that were moving, right? It'd be virtually impossible for the poles to have moved that much, but what is moving is the continents, right? And so this was a lot of the early evidence for continental drift. And this is, again, this paleomagnetism idea is certainly the most important piece of evidence that we have. So Wegener's hypothesis, if you recall from earlier, is simply, if the magnetic poles remain constant, it's just the relationship or the apparent movement of the continents to the actual poles themselves. So we look at, if we look at kind of this bottom image here, and this goes back to Lake Pangea, where all the continents are, essentially are joined as one. And this actually then makes a lot more sense, right? But it was the motion of the continents, again, not the magnetic pole itself, okay? And I can probably guarantee you there's going to be a question that kind of echoes that idea pretty similarly. So remember this image, and certainly remember this slide. All right, magnetic reversal seafloor spreading. So we started noticing that as we're testing seafloor samples, right? So our core drillings, we started noticing differentiations essentially in levels of magnetism. But one thing we also learned is that the polarity of the Earth's magnetic field changes over time, right? So about every million years or so, the magnetic field of the Earth, it switches, right? So north becomes south and south becomes north. So it's just our magnetic poles, which is, again, geographic poles, they're there, they're going to stay. It's just that magnetism will actually change. And so what we call these periods, so every 1 million years, we're give or take, right? These will flip, and the time increments, the magnetic time scale you see here, we refer to each of these periods as crons, right here. So each cron is just that period of rocks, right? We're noticing different orientations, different strengths of polarity. It's just that period where the rocks will point to north, at least for that time. So we refer to these periods, at least as it is today, as normal polarity. And it's just simply, the polarity is the same as the current field, right? But then we also have the reverse polarity during these periods of magnetic reversals. So this was, there's also a gentleman or two, Fred Vine, and there's a question about this on your exercise, D.H. Matthews, where basically when they were mapping the seafloor spread, and let me move this, that's what this is supposed to show, right? So this is your mid-oceanic ridge here in the middle. As it spreads, these color-coded pieces are simply just periods of normal magnetic polarity, right? So there's no difference between green, yellow, red. It's just that these are the periods in which they're pointing, to the direction it is today, north. But they shift, right? So your reverse magnetic polarity are these white or gray pieces here, and that these, as he was testing, or they were testing, these are periods of high polarity or interaction with, high interaction with Earth's magnetic field, but then the whites are the kind of these low interactions. And what they noticed were these essentially, they overlap. They're the same periods of these magnetic reversals, right? And so this kind of gives further evidence when we kind of then extrapolate out the direction orientation of the rock formation, of where they were oriented, where they were pointing, as to the motion, excuse me, of the plates, of plate tectonics. Also, there are shorter intervening periods within each cron, not within each, but there can be shorter intermediary periods within a cron of, short period orientation of, or not orientation, excuse me, of reversals of the magnetic field, right? So about every within these, they can last essentially 200,000 years. Again, yes, that's short, geologically speaking, at least. All right, last, what drives plate motions, right? And this brings us back to our friend convection, right? So we talked about this kind of at length when we're within our atmospheric section. This doesn't go away. Convection essentially is the mechanism that early continental drift theorists lacked when they were trying to describe their theory, that until you could actually have that mechanism, there's going to be the shortcoming. And so what we assume today to be true is just the convection within the Earth is driving the plate tectonics, right? So it's if we look at this image, and we saw something like this when we were talking about the atmosphere, but convection is kind of the classic example, this pot of water sitting on top of the burner. But if we view this as the burner being kind of like the Earth's core, right, that's where all the heat is coming from. As the heat heats the surrounding, the core heats the surrounding environment, right? The mantle, it rises because it becomes less dense. At some point, it's going to cool because it's getting further away from its heat source, and it's going to sink down again, right? So it just follows a circular pattern, right? So the core heats the surrounding environment, becomes less dense, it cools, and then it sinks, right? So these are just the basic processes. These are, this is the lava, this is the rocks. But when this has then the interaction with the surface with our tectonic plates, right? And it's just having that interaction and essentially creating this process of creation and destruction, right? So we're going to talk about now just two real quick key terms: slab pull and ridge push. I just realized those were in different fonts. Simply just this. So this is like that downward arm. Let's see if this will work. No, didn't work. I don't know how to make this move backwards. If anybody knows, let me know. So this is the downward arm of that convective cycle, right? It's what's had been cooled and is now sinking down. There's two different forces. Let me move this. So first we have slab pull. Excuse me. So slab pull is simply just, it can be like a gravitational force, but essentially it's convective force in that, the oceanic slab in this case, it's just cooler than its surrounding or underlying environment, the asthenosphere and the mantle, where this is really hot, right? So anything cold, if we go back to like air parcels and air columns, right, is gonna sink. And that's all this refers to. And now there's some sort of interplay too with the angle and the slope at the trench. But really the only thing, and the most important thing we need to know here is essentially this is the plate, the lithosphere is being pulled down because it's cold and because it's dense, right? We talked about that earlier in the presentation. The other piece of this is the ridge push, and this is purely a gravitational component. And that along these mid-oceanic ridges, these are basically mountains, right? So as the upwelling of magma is allowed to be, I say allowed to be forced up, because the spreading, the pulling apart of the plates here, the crust becomes thinned. If you're thinning out the crust, it's less downward pressure on the mantle, which then basically allows more magma to come up. It has this upwelling effect, creates kind of this ridge, this mountainous effect. Well, like everything else, gravity applies, right? And so as the plates are being created at the top of this mountain, at the top of this ridge, it's going to essentially fall down or tumble down a slope, right? In some cases, it's a fairly severe slope. Most of the time, it's a pretty gradual kind of deal. It's not like you're going to walk out or swim out, I guess, to these ridges, and they look like extreme cliffs and mountains, though it certainly can at points. But most of them are fairly gradual. But basically, if you think about the immensity of these plates, it forces, it pulls. I don't want to use the word pull because it kind of construes with slab pull, but basically it will pull itself downward. Let me move this again because of gravity. All right. So two different forcing mechanisms acting upon again, these serve as kind of that downward arm of the convective cycle. So a couple of things, and then we have two more models to talk about real quick, and then this will be over. So things that we know, right? So the convection in the mantle, we know that convective flow is the underlying force of the plate movement, right? And that's illustrated within this GIF here. We can kind of see this circular effect. We have our mid-oceanic ridge here. It's kind of a cool GIF, right? Here's our core. You have this plume, this heat transfer, right? Makes everything less dense. It rises because it's been thinned here at the crust. It's allowed to essentially come through the crust, create new lithosphere as it's pulling apart this way, and then also this way at the ridge. We have the slab pull here. We have these gravitational forces here coming down. As it gets older, it gets cooler, it gets denser, it's interacting on the far left here and somewhere over here on the right. It's subducting, and it just recycles, right? It destroys itself. This destructs, called a destructive margin, back into the center of the Earth. All right, cool. So we know that. So this is kind of the common theme in the next couple of slides. We talk about this dense slab, oceanic slab, or whatever it may be. But we know that convective flow is the most important. There is a note here. Convective flow is also the main mechanism which to transport heat away from the Earth's core. So essentially heat from the core comes up, but also radiates out, right? So it basically escapes the surface and radiates out into space. All right. So to explain these, we also have two different models. We have the whole mantle convection model here, and then we have the layer cake model, which is awesome sounding. So first, and these are the last two slides, I promise, the whole mantle convective model, also referred to as the plume model. They call it the whole mantle convective model because it essentially incorporates the upper mantle and the lower and mid mantle, right? So basically what differentiates this approach is essentially it's a churning of the whole mantle as one, right? And so these first couple of points is simply that what we've been talking about. It doesn't really fit on here much, but you have, if you follow these arrows, right, you have the plate subducts down into the asthenosphere, down into the mantle. You can kind of see pieces here where it starts to kind of break up. This is the downward, right? If we follow the arrows, things get heated up again, and they essentially get forced back up, right? So if we follow this, it's just a big circle, right? The same thing here. You follow this line, it's a big circle, right? That's the convective flow. And so this whole mantle approach is essentially from basically the top to bottom. It's all involved, it's all churning, right? Two pieces of this, we have our narrow tube plumes, right? So these are the, what's responsible for the volcanism. These are, your volcanic island chains, continental island chains. But these originate in this particular model from the Earth's core, or at least within the boundary, the core mantle boundary. So it has kind of a direct connection to the core here, right? And that's different in the next model, so it's kind of just a little point of detail. And then you have, let me move my picture here, you have the large megaplumes. Essentially, instead of being these kind of skinny, narrow ones, you have these huge kind of reserves of magma sitting, somewhat, pretty far, but below the surface. But they're so big that they essentially have the effect of anything above it, this space, all the material above it, essentially forces it up, right? And it forces then, if it's forcing the material up here, it's also forcing the Earth's crust up above it, right? And so we see these in the Pacific Basin and in Southern Africa, right? And so these are kind of two distinguishing characteristics, these plumes, within this convective model approach. All right, and then last, you have the layer cake model. Very similar, right? The difference in this is simply that the activity, this circulation, this convective circulation, is only occurring in the upper mantle, and that is not occurring in the kind of medium lower mantle pieces. So I think you could tell the difference pretty easy. So that's where the name layer cake, comes from. It's simply just these layered components that don't really interact. Right, so same concepts, right? So you have the recirculation of the subducted material, right? It gets cold and dense, hits the trench here, subducts, essentially gets recycled back into the asthenosphere. It is cold, it gets warmed up again, and it rises to the surface. Biggest difference here, basically it's just not a stirring of the whole system, right? It's layered, it's only occurring, all these processes are occurring only in the upper reaches. When we look at your plumes, the differences here are you don't have the connectivity to the Earth's core, right? These mantle core boundary zones. And so instead, everything is occurring, you know, I say shallow, but it's certainly not shallow in kind of real terms, but relatively kind of in shallow depths, right? And so we think of these upper mantle layers being very dynamic because this is where everything is occurring. Meanwhile, the remainder of the mantle is very sluggish, not a whole lot happening, right? So the result of that is volcanism as a dynamic process. All the material is being supplied simply within the upper mantle and nothing from below. Okay, so that is it. I hope it wasn't too painful. I don't like sitting in this room talking to myself. It feels incredibly weird, but it is what it is. So please ask any questions, read your books. I know many of you do not like reading your textbooks, but I promise you it's going to help. So please read. Come to our Wednesday WebEx gathering with questions specific to the presentation, and that should be incredibly helpful. All right, see you next time. Thanks.